Welcome back to the second video of L'Hopital's rule. In the first video, I laid out the basic premise, which was that if you had a limiting function or a limit function that was indeterminate in the form 0 over 0, you could instead calculate that same limit by finding the limit of the ratio of derivatives instead of the ratio of the original functions. And it turns out that that works for infinite over infinite as well. You can also, might be worth mentioning now, you can actually do this over and over and over again. If in fact your derivative ratio is also indeterminate, you just take the derivatives again. So if you started with a cubic over a quadratic, that's indeterminate as x goes to 0. And so then you take the derivatives and you get a quadratic over a linear function, which is still indeterminate. So you take the derivatives again and you get a linear function over a constant, which is not. So you can repeat this over and over. We're going to quickly look at three new functions or new setups. And I've written infinite to the 0, but the examples that I'm going to show you are 0 times infinite, 1 to the infinite, and 0 to the 0. I'm going to try to go through them fairly quickly to keep this video short. So we'll start with the limit of x squared natural log of x as x goes to 0 from the right. You'll notice x squared goes to 0, natural log of x actually goes to negative infinity, doesn't matter. And so what we want to do is we want to figure out how to rewrite this function so that it looks like either infinity over infinity or 0 over 0. So we're going to rewrite this as the limit as x goes to 0 from the right of natural log of x divided by 1 over x squared. Natural log of x, negative infinity. 1 over x squared, positive infinity. This is infinite over infinite. And therefore, we can do L'Hopital's rule. The derivative of natural log of x is, excuse me while I write, 1 over x. The derivative of x to the negative 2 is negative 2 x to the negative 3, and I'll just write that as a fraction. A little bit of algebra gives us 1 over x times x cubed over 2 with a negative out front. A little bit of simplification gives us that this limit is in fact equal to 0. So let's take a look at another example. 1 to the power of infinity. As x goes to infinity, 4 over x goes to 0. 1 minus 4 over x goes to 1, raised to the power of infinity. So what I'm going to do is I'm going to define L as this limit. As you probably remember, anytime we've got power, sometimes natural log comes in handy, or any sort of log for that matter. I'm going to take the natural log of both sides. The natural log of L is equal to the natural log of that limit. I am allowed to move that natural log inside. That natural log does not affect the operations of the limit, and that means that I am allowed to move the x out front. Hey, now I've got infinity times 0, infinity times 0. So I just want to make this 0 over 0. This becomes the limit as x goes to infinity of natural log of 1 minus 4 over x. That has a limit of 0. Divided by 1 over x. That has a limit of 0. So taking the derivatives, I'll just keep going down here. This equals the limit as x goes to infinity of, well, the derivative of x to the negative 1 is negative x to the negative 2. The derivative of natural log is 1 over times the derivative of the thing inside, and the derivative of the thing inside is negative 4 times negative x to the negative 2. So that is 4 times x to the negative 2. I'm going to reduce the x to the 2's. And what I end up with is the limit as x goes to infinity of 4 negative 4 over 1 minus 4 over x, which is in fact negative 4. Now careful, I'm not quite done. This means that the natural log of my limit is negative 4, which means that my limit is e to the negative 4. So again, I had a power. I use natural logs to move the power out, and now I can do fun things. Let's do one more, 0 to the 0. And again, I'm going to call this L because I have a power. I want to use logarithms. The natural log of L equals, skipping a step, the limit as theta goes to pi over 2 from the left of the natural log of cosine to the cosine. This is equal to the limit as theta goes to pi over 2 from the left of cosine theta natural log of cosine theta. And of course, this is 0 times the natural log of 0. This is 0 times infinity. So what I want to do is make it infinity over infinity. As theta goes to pi over 2 from the left, natural log of cosine theta divided by 1 over cosine, which is secant theta. So I've got infinity over infinity. Let's do those derivatives. And we'll just keep copying that out over and over and over again. 1 over cosine times the derivative of cosine divided by the derivative of secant. Let me check my notes and make sure I did that right. And a quick thought, which is why when I looked at that, I thought, wait a second, that's secant times tangent. Of course, you knew that. You're shouting at the screen, no, Mr. Arberding, no, Mr. Arberding, it's secant times tangent. And so sine over cosine is tangent, and what we get here is negative 1 over secant, which is negative cosine of theta, and of course that is in fact 0. Now again, careful. The natural log of my limit is 0, which means my limit is e to the 0, which means that this, in fact, has a limit of 1. If I were to graph cosine to the power of cosine, see what it does as I approach pi over 2 from the left, it in fact equals 1. All right, quick recap. What have we got? Where's my last slide? There it is. If I have infinity times infinity, I move one of them to the bottom so that this becomes infinity divided by 1 over 0. I take the reciprocal of one of my functions and put it on the bottom. If I have 1 to the power of infinity, I take the natural log and I can bring the infinity out front, and I get infinity times natural log of 1. Again, remember, we're just talking about limits. We're not talking about infinite numbers or natural log of 1. Really, we're just talking about limits, and that becomes a limit of 0 over 0, which is indeterminate. And if I have 0 over 0, again, I can take the natural log. And just a quick reminder for both of these, once I find my answer, the natural log of my limit is equal to whatever number I got, which means that my actual limit is e to that number for both of these situations that use the natural log in order to make it doable. All right, that's all I've got. Thank you for watching, and I hope you learned something.